Now, LoG filter, I think we have discussed this earlier, how to get Laplacian of Gaussian. You compute second derivative, but there's a very interesting way how you can optimize computation of this Laplacian of Gaussian. So this LoG filter, and you can actually just compute difference of Gaussian. And that is a very good approximation for this Laplacian of Gaussian. And if you compute difference of Gaussian, because you have two different Gaussian curves, and you just perform difference between those two, that will give you this DOG filter, which is called difference of Gaussian. So in this case, it's interesting because you don't have to compute derivative anymore. Because to compute LoG, you have to compute second order derivative, remember? So it will be second order derivative of your Gaussian function, and that's computationally expensive. So if you want to save some cost, this is a very interesting trick. And let's try to understand how a DOG is actually approximation of LoG. And I think then we will end it here. We are almost out of time. Let me cover this this part. Okay, so let's say you have a Gaussian curve, a Gaussian function, which is shown in the green. Okay, so this has like some kind of standard deviation, and so let's say mean is 0, which is fine. Then what you do is you reduce the standard deviation of that Gaussian, and what you will get like this red curve. Again, this is a Gaussian, but with a smaller standard deviation. All right. Now what you do is you just take difference of these two. You subtract these values. And what you will get is you will get this blue curve. I mean, I think it's interesting. You can do the math, but this is exactly what you're going to get. Okay, at this location, you can see if you compute the difference, it's this region over here, right? But it's negative because the green one has negative value, so it will go down. Okay. And if you compare this with the inverted hat or inverted Mexican hat, this looks exactly like that. Okay, you have 0, then slightly positive values, then very big negative values. Again, the symmetry of that. So this you can use in place of your Laplacian of Gaussian. It saves like a lot of computation cost.